model performance. So yeah, as I mentioned, we're going to be doing both the theoretical and a bit of practical deep dive here, but really mostly focusing on the algorithms. On the agenda, we have 4 items. The first one is we're going to talk about 2 main causes of potential model failure. And here by failure, I mean significant drop in machine learning model performance. Then in the second part, we're going to focus on one of those causes, which is the covariance shift. And we're going to talk how it can potentially impact model performance. And we see that the story there is not going to be that simple. And the impact can be both positive and negative, depending exactly on the type and place where the covariance shift actually happens. And then once we have that and we've built kind of an intuition of how covariance shift impacts model performance and what is also the role of uncertainty and all that, we're going to talk about our 2 main algorithms that actually help us quantify the impact of covariance shift on model performance. And for regression, we have an algorithm called DLE, which stands for direct loss estimation, that helps us quantify the impact of covariance shift on model performance. You're going to hear that sentence a lot here. For regression models and for classification models, we have confidence-based performance estimation that does the exact same things, but for classification models, and here it works both for multi-class and binary classification models. We're going to be focusing on the binary example just for the sake of simplicity, but everything here will generalize also to multi-class problem. So now let's get started with the first thing, which is the 2 main causes of machine learning model failure. Just before we do that, we'll do a quick refresh of what are the actual moving parts for our machine learning model. What are the things that we ingest? What are the things we're trying to achieve with supervised machine learning? So the first thing is that there exists some kind of true pattern in reality that we're trying to capture. In our example here, we have just one feature X, and we're trying to predict a binary outcome. And we see that as feature X increases, we have this kind of sigmoid pattern that the probability of a positive class increases. And then if X is very high, also it's almost, the probability actually decreases, and the probability of negative class is almost 100% if X is very high. And this is the pattern that our model will try to capture based on the data we have. And the data we have is the sampling mechanism. So it's the way we sample the data from our population. We never have access to the full population, but we have centered sample of our data, for example, our current customers or all the past events that we managed to collect. And that just forms our data that we then use to train our model. And then imagine that we did train the model, we managed to capture correctly the pattern that we see in the top of the slide. What can then happen? The first thing that can happen is so-called covariance shift. Covariance shift happens when our sampling mechanism is changed. It's not something that we necessarily control ourselves, but it might be that we deployed our model in one country, but so we trained the model in one country, but then we need to deploy it in another country, or just a different segment of population, or even the segment is the same, but slight distribution of, let's say, age changed, or we deployed our model on one machine and now it needs to operate on a slightly different machine. Then we see that there is a difference in sampling, and that will also influence how our data looks like. And not only the data, but also the actual targets or the labels that we have, and the class balance might also change. And that may or may not impact the actual performance of the model. And I'm going to delve deeper into that in the second part of the presentation. But now let's focus on defining it fully. So the covariance shift is basically the change in the joint model input distribution, so the probability of all x's. And we see one example of that in one dimension is that there's the mean mate shift, but it also might be any other structural change in the joint model input distribution. And it might be that even on every specific dimension, you will see that the distribution does not change, but for example, the correlation between different features changes. Then the second reason why machine learning models may fail is so-called concept drift. And here, what changes is the actual true pattern that exists. Let's say that people used to default on loans when they made less money, but this for some reason no longer holds. If that happens, the pattern that our model has learned is no longer fully relevant for the real world that the model is operating it. So it's very likely that the model will actually fail. And that's one of the reasons why we're not focusing on it. Another reason is that to really quantify concept drift, we do need to have access to labels. Why is that? Because concept drift is simply defined as the change in the relationship between the target and the model inputs. So it's the conditional probability of the target given the feature vector. And if that happens, we really cannot quantify it before we have access to the targets. And we do need to know the model performance and quantify the change of model performance before we have access to the targets. And I'll explain that in the next slide. I hope anything is clear. Again, if you have any questions, do put it in the Q&A and I will answer the questions at the end of the presentation. Now let's just visualize the concept drift to just give a bit more of an intuition. So here we see that the actual true class boundary that exists in reality was this kind of vertical thing that goes like that. Vertical, vertical. And then due to some change in how the world operates, maybe something like a pandemic or some other huge event, or maybe something slower that actually changed the actual concept gradually, we see that instead of having this class boundary that goes like that, we have now basically a horizontal class boundary. And of course, if the model learned the first boundary, it's going to operate really badly on the second boundary. So this is concept drift. This is not something I'm going to focus on. Now we're going to be focusing on the first reason why machine learning models can fail, which is the covariance shift. And before we go into really discussing the intuition of how covariance shift can impact model performance, we need to talk about one really important thing, which is we generally want to catch model failure or catch change or deterioration in model performance before there is business impact. And what you see is basically on a timeline. The first thing we get is we get model inputs. These model inputs are then fed to the model. The model will make predictions. And as the predictions are made, then these predictions will be processed in some way. Maybe it's going to be a credit scoring model. The predictions are credit scores. These predictions will then be used to either deny or grant loans. For predictive maintenance use cases, you're going to get model outputs, whether the model needs maintenance or not. And based on that, the maintenance will be performed or not. So there's going to be some kind of business impact that the model will basically create. And what we want to do, and only once this model business impact happens, we then possibly get the targets. So in case of loans, we're going to have to wait quite a long time, let's say 2-3 years, whatever is the length of the loan, to see whether the person actually defaulted on it or not. And then we're going to keep on making more and more predictions in that time. And what we want to do ideally is catch model failure before there is business impact. So before the loan is granted, or not as ideal, but also quite okay, shortly after the loan is granted. So then we can stop the model from operating, let's say, for this remaining 2 years and granting more and more loans. So we want to catch model failure as soon as possible to minimize or ideally eliminate the business impact. And that also means that we never have the targets before it's too late, because if we have the targets, the model already acted and we got some feedback from the real world. So we have to focus on trying to estimate the impact of covariance shift on model performance without access to targets, because basically by definition, if we have access to targets, there's already business impact and the damage has been done. Hope that's clear. Now, let's talk about the intuition of how we can quantify the impact of covariance shift on model performance without access to the target data. So the first thing we're going to do is we're going to look at model predictions. We have this beautiful dragon fruit picture here, which just quantifies or shows what is the confidence of the model depending or when in the model input space a given data point is located. So what we did here is we trained a model. It was, I think, a nonlinear SVM because it gives very nice smooth shapes. And what we see, it's just a simple XOR problem. And what we see is that if there is a concentration of data points from one class, then the model tends to be very confident about its predictions, that it's very likely that their predictions there are going to be positive or negative. So the predictions are concentrated around either being predicted probabilities are concentrated around being very close to either 1 or to 0. And the confidence is basically just a simple measure of how far from 0.5 the prediction is. So if the model confidence is 0, the model predicts probability is 0.5. If the model predicts probability is close to either 0 or 1, then the confidence measure that we see here is going to be very close to 1. So basically just like an absolute value, but centered at 0.5. And what we see is that we can actually look at this model confidence as kind of the proxy for potential model performance. To build a bit more intuition, imagine that we take a point that's very close to the class boundary. Then there's not much information to go about to try to predict whether the data point is going to be positive or negative. If it lies exactly on the class boundary, it's basically a coin toss, it's 50%. So there we actually expect, for these data points that are close to the class boundary, we expect performance to be very low because there's no information to really use to try to predict the target. And then we see that also the model confidence is going to be very low. We see this intense ping there. And then also, if we see kind of potential points that would appear, let's say, around -3 point in the feature space, we would also expect the model to really not know what to do, and we would expect to see very bad performance because the model was not trained on the data. So we can use then that model confidence as a proxy for the expected model performance. But what is the role of covariance shift in all that? So the main point is that covariance shift is change in the distribution of data in the model input space. So what you see here is on the test data, where we tested our model and we decided that the model performance is satisfactory. We had certain model distribution that's kind of wide and covers most of the green regions where we expect to see high model performance. But as we deploy our model to production, for one reason or another, we see that actually most of the data points are concentrated very close to 0, 0 region, which is exactly in the middle of the red zone, where it's very hard to predict whether a given data point is going to be positive or negative. So then we expect, if we see that kind of pattern in our covariance shift, in our drift, we expect to see a drop in performance. Now, kind of on the opposite side of the spectrum, if we see that there is significant covariance shift, but the data happens to drift to regions where the model is very confident of its predictions, we actually expect to see either no significant change in model performance, or in very extreme cases like the one you see here, we would actually expect to see an increase in performance, which means that covariance shift is not always bad news. If the data will drift away from the class boundary into a region where the predictions are very easy to make because they are all, for example, here 1, then we might actually see an increase in performance and potentially increase in business impact, which means that covariance shift, not always a bad thing. And then last kind of typical use case we might see is drift to regions that were not seen or not properly seen during training. So there was not enough data to really capture the correct pattern in that region. If that happens, what we expect to see again is, because the model didn't learn the pattern there, the model will probably predict badly. And again, as we see here, if the data drifts to this free region, we will expect to see a drop in performance. The model is basically predicting random value there, and we will expect model failure actually. So now, as we covered the actual intuition of how we can think about the relationship between covariance shift, the model certainty or model confidence, and expected performance, let's try to formalize this thinking with our first algorithm for regression model called direct loss estimation. So we'll be able with this algorithm to take the model predictions and somehow turn them into expected performance of the model, given the current feature distribution, so given the covariance shift we're experiencing. First, what can we estimate with DLE? So we can estimate basically any metric that we use as long as it can be quantified on an instance level. So we can look at root mean squared error, which can be calculated on an instance level when it's just squared error, and we're going to aggregate it over a certain period of data, or certain number of data points, we get root mean of that squared error. Same for absolute error. We can take the mean absolute error, and again, for logarithmic errors, the same thing follows. So basically, any metric that's really used in practice for evaluating regression models. What do we need to use DLE? So first thing is we need so-called reference data. Reference data is the data for which we do have the targets and we are happy with performance. So we have performance that we can treat as a benchmark. Typical choice for the reference data is the test set, because this is by definition a data point for a data set for which we have the targets, because we were able to actually test them all on that and evaluate the performance. And after we have evaluated the performance, we are happy with it. Then the second thing we need is the actual data in question, for which we try to estimate our performance. So this is just the monitor data, the production data that just streams in as we make the predictions, either in batches or in streaming. It really doesn't matter. Here, importantly, we don't need the targets because we try to quantify the impact of covariance shift on performance before there is business impact, so before targets arrive as kind of a feedback from the real world. And then the last thing we don't really need, but we just need to specify, is how we want to aggregate our data. So imagine that instead of trying to just aggregate data in some chunks, we want to estimate the performance for every single data point. This is something that we could potentially do, but unfortunately in practice, the estimation error of that performance is going to be very high just because of the stochastic nature of the data. So instead, what is more practical, we're going to look at, let's say, collection of data points, let's say a day of data, an hour of data, or last 1,000 data points. We're going to aggregate those, and we're going to assume that the performance for that specific chunk is reasonably constant, or it's approximately constant, which is generally a very correct assumption for almost all use cases. And then instead of looking at very uncertain estimations for every single data point, we're able to very significantly actually reduce the uncertainty of performance estimation. And we're going to be looking at the chunks of data. And interesting thing also in NanoML, we also output the confidence bands. So you know that if your chunks are very small, you will actually get very big confidence bands, which means that you shouldn't trust your predictions too much and potentially try to aggregate data on a higher level to get more points per chunk. All right, so now, as for the assumptions, there's already really one assumption that we need to be aware of, which is that there is no concept shift. One thing that I already mentioned, concept shift can also impact performance. So this is one of the things when we want to get good performance estimation. The only thing we need to do is basically assume that there is no concept shift, and then we can really use DLE to get good performance estimation. Another thing is that concept shift itself, so the change in the conditional probability of X given Y, will also impact the uncertainty distribution or the uncertainty landscape. So the very thing that we want to actually leverage would have changed, and there is no way to really quantify how that change exactly happens before we have the targets. So we're going to assume that there is no concept shift. This is actually not a very strong assumption for most of the use cases. For any use cases that deal with physical world, the physics doesn't change, so concept shift is very, very rare. For any customer analytics use cases, you might see concept shift, but it's something that generally will be very well known and obvious from business perspective. Let's say that you train a model in Germany and then try to deploy it in China. Of course, the consumers there react differently, think differently, work differently. So you will obviously expect to see some concept shift, but that barring these kind of extreme events or extreme changes, concept shift rarely happens in practice in a way that's very, very influential on short time scales. And we also have a way to measure concept shift, but that requires targets. So this is something that we rely on, that it doesn't happen too often. And as long that it is the case, then we can wait for the targets and actually quantify the impact of concept shift as well. But enough about concept shift. Now, let's assume it does not exist for the time being. There's no concept shift. The actual pattern that the model has captured is still correct. What do we take as inputs? First thing is we need to take the model predictions. Whatever our model predicts, it's a continuous real valued number. we take that. We also will take all the features that the model consumes, and we also take the target, also known as the ground truth, for the fitting part, so only for the reference dataset, because on the reference dataset, we're going to fit the DLE. It's also a machine learning algorithm, and we're going to learn how the model uncertainty, what is the model uncertainty, and how it maps to expected model performance. Then how is performance estimation possible? We already talked a bit about the intuition from kind of classification variant, but now let's talk how it exactly works for a regression use case. So imagine that we have this very simple regression problem when there is just one model input, the value X, and we're trying to predict Y. And what we see that there is basically a perfect linear relationship. We capture all information that we have in our dataset to create the best estimator possible, which happens to be just linear regression because I created that data to follow regression, to follow a linear pattern. But we also see another very interesting thing is that the data points seem to be more dispersed the closer they are to the X equals to 0. And if you go higher, where X is close to 10 or equals 10, then we see that basically the regression is perfect and there's almost no noise in the data. And that means that if we pick a point where value of X is close to 0, let's say it's 1, we expect to see a bigger error, so lower model performance. Whereas if there's a lot of data points that come from a region between, let's say, 9 and 10, we expect to have very good predictions, so also very good model performance, very low errors. However, we define our error, whether it's absolute errors, with error, doesn't matter. And just to validate that this is indeed the case, what I did here is I calculated the rolling mean where we roll over X's for each 100 data points. And I calculated the expected error, sorry, not expected, actual realized error that we see, absolute error of predictions. And we see that indeed, for lower predictions, we observe higher errors on average. And as we increase our value of X, then we see that the errors get lower. And this is really the key intuition, is that the dispersion of points kind of corresponds to uncertainty. There is a measure that we can actually measure that based on where data point is in the model input space, we can find what is the expected error of that data point based on how much information there is about the actual target in that region in our model inputs. To visualize it in 2 dimensions, imagine that now we have 2 features. Of course, it generalizes to hundreds, thousands of features, no matter how big our model input space is. And we can then quantify this expected error, and we'll see how in a second. And then imagine that on the test data, we have data points distributed as such, the blue points. And as we deploy our model to production, we see that unfortunately, a lot of data points actually drifted to the red areas. And that means we expect to see a drop in model performance for a given chunk of data. So we're going to aggregate all those predictions, and we're going to get the, let's say, mean squared error or mean absolute error. And that's going to be the metric we're going to be using, we're going to be estimating. And it actually happens that as long as there's no concept drift, this is the true expected mean absolute error or mean squared error that we expect to see once the targets arrive. Now the algorithm itself. We have very detailed documentation and blogs about how the algorithm works in detail. Everything is like, we do open science, we're not hiding everything, so you can actually see how it works. And DI is also fully available in our open source and the cloud product. But how it works. So first thing we're going to do is we're going to calculate the loss metric on the reference data. Again, for reference data, for example, our test data, we have the target data, so we can just simply calculate the actual loss metric we're using, such as MAE. We're going to do it for every point separately, so we're going to get all the absolute errors. Then we're going to train a model to estimate this loss metric, absolute errors, using the features that the actual monitored model consumes, and the monitored model predictions as well as a feature. Because generally, these predictions can also be informative of the error itself. And we see in practice that they are. Then we're gonna we're gonna take that regressor. Let's say it's a gradient boosting model. Actually, we use in our open source and the cloud product, we all use the gradient boosting models. And then we can use that model, the DLE, to directly estimate the loss on the monitor data. So for every data point, we're going to estimate what is the expected absolute error there. And then once we have all those absolute errors for a given chunk of data, let's say the day of data, we can aggregate that data per chunk. And that is the output that we have, the expected absolute error, mean absolute error per chunk. How does it look like? So here I wanted to show one thing that might not be obvious to some of you, which is that just because there is covariance shift, it does not mean that the performance has dropped. What you see on the left side is an overall measure of change in the joint model input distribution, the data structure. So just a way to measure multivariate data drift. It's called PCA reconstruction error. It's one of the algorithms that we have for multivariate drift detection, for multivariate covariance shift detection. And the higher it is, the stronger there is a change between a given chunk and the reference data in terms of the data structure. So data might be distributed differently, look differently. We know that the internal data structure has changed if that value goes up. I'm not going to go into details of how it works, but of course, we can share our resources for that later. But what I wanted to convey here is that as data drifts and we see that there is actually very strong covariance shift, it does not mean that there is any issue with model performance. And even more interestingly, you see that there are two spikes in terms of MAE here, but they don't really correspond to anything specific in terms of data drift. And you really need to quantify the impact of data drift on performance or covariance shift on performance. You cannot just rely on covariance shift measures as a proxy for performance because there's really basically no relationship whatsoever. And we need to be able to find the performance, expected performance as fast as possible. And there is a place for drift detection, mostly as a kind of root cause analysis tool, where we can try to figure out which features are exactly drifted, how they are drifting, what is the actual main reason why our models are failing within the umbrella of covariance shift. But for trying to estimate whether performance is good, we need to rely on algorithms such as DLE to really know what is the impact of covariance shift on performance. So that's DLE. That's how we estimate the impact of covariance shift on model performance without access to labels in a way that actually gives you expected performance in the metric of performance. And that is a much more accurate measure of what is the current level of your predicted performance compared to just doing simple covariance shift detection or data drift detection. So now the last part is how we can quantify the impact of covariance shift on performance for classification models. So here we have confidence-based performance estimation. We're very creative with names, as you can see. And what it does is basically what it says it does. Let's talk about the same format as before. First thing is, what can we calculate? So we can calculate, first of all, the confusion matrix for both binary and multi-class variations. I'm going to be focusing on binary just for the sake of simplicity here. We can also calculate precision, recall, accuracy, basically any metric that you can get as long as you have the confusion matrix, because we'll actually get the confusion matrix first, and then we're going to be computing any metric we want. You also can compute metrics that need a range of confusion matrices. So basically, you will change the thresholds, you will get different confusion matrix, and then we construct a curve such as ROC-AUC or ROC curve. We can also get those metrics, so ROC-AUC, average precision, etc. And the last thing we can get, similarly actually to DLE, is we can get the business impact. So for some use cases, let's say for credit scoring, you know what is the actual expected monetary loss if somebody defaults on a loan. And you also know how much money you're making on average per loan that's given. If you know that, you can estimate not only the machine learning metrics, but we can also estimate that business metric, which is how much money the model is making per chunk of data per day of operation. And this can be very useful for communicating with business stakeholders, because then you also increase the visibility of your model. And you can say that the model that you deployed to production today made, let's say, 50,000 euros, which is obviously a very useful thing for you just from personal career progression perspective, because you can really show the impact of, that your work has. Assumption is exactly the same thing. There's no concept shift. Inputs are very similar to DLE, but I wanted to mention one specific thing here is that we not only need the model predictions, 0 or 1 for binary prediction use case, but we also need the model scores or the model predicted probabilities, because we're going to be leveraging those instead of building our model. We're going to be leveraging those to estimate the uncertainty of each prediction. And then the last thing is that we need the targets for the reference data set, just as before. Now I'm going to skip the intuition part because we already covered the intuition at length, both in the section 2 about how coverage shift can impact performance and in DLE. And the intuition is exactly the same. If the models are more uncertain, then we expect to see a drop in model performance. What is the kind of recipe, the actual algorithm that we're using? So it has 5 points. The first one is we just take the model predictions and the predicted probabilities. Then the predicted probabilities need to be calibrated. Calibration means that we're going to take the actual predicted probability that your model outputs, let's say 0.7, and we're going to ensure that this 0.7 actually corresponds to the frequentist definition of probability, which is that for a large number of samples, so let's say we get 10 million data points that all out 0.7, we expect 70% of them to turn out to be positive. This is what means to have 0.7 probability according to the frequentist definition. And we're going to ensure that the model predicted probabilities actually follow that definition in the aggregate on average. And I think also in expectation. Yeah. And then once we have those calibrated probabilities, we're going to find the expected confusion matrix for every point. This is really the magic point when we're going to turn those predicted probabilities and model predictions into a confusion matrix for every data point separately. Once we have that, we can then aggregate that confusion matrix for a chunk. So instead of having just, let's say, 1,000 different instance level confusion matrices, we're going to get one big confusion matrix per chunk. And once we have that, we have the expected confusion matrix for a given chunk. We can just use it to calculate any metric that we care about, including the business impact, as long as we know what is the impact of each true positive, false positive, etc. So now we're going to go over each of these points step by step. It requires a bit more nuance than the DLE, where we just train the model to predict the errors. Here we have a few more points, and I'm going to skip point number 2 at first. We're going to assume that the calibration is already there, and then we're going to talk about all the other parts. So now for how we actually do it. We're just going to start with the confusion matrix, and we're going to try to fill it even though we don't have the targets. Normally, we have the actual column here, so we need to know what the actuals are. But we're going to, for the time being, actually, for this algorithm, we're going to assume we have no targets, so we need to do something else there. And it turns out we can actually do it, which is really the magic behind it. So the first point is that we're going to take a look at the model prediction, and let's say that the model makes a positive prediction. That already gives us some information about the confusion matrix, because if the model predicts positives, it means that it's definitely not a negative prediction. So we already know that it's not a false negative. We know that it's not a true negative. So in both of those cells, we're going to put 0. Then we also know that the model predicts, let's say, 0.7. And for the time being, I'm going to assume that these probabilities are perfectly calibrated. So the 0.7 actually does correspond to 70% chance that this prediction will turn out to be positive. And now remember that at the end, we're going to put those predictions together so we can work with an average. So what we're going to do is we're going to say that on average, in expectation, there is 0.7 of true positive here and 0.3 of false positive. And as we aggregate the predictions in a chunk, we're going to get to an expected confusion matrix following the exact method like that. So then for the second prediction, we do the same thing. It's 0.4. It's a negative prediction. We put 0.4 in false negative, 0.6 in true negative, because this is the remainder. 1 minus 0.4 is 0.6. For the first prediction, the same, etc., etc. We should do it for like a few hundred data points more. But now let's say that our chunk is only 3 data points. And then once we have that confusion matrix, we can then just take a metric, let's say accuracy, and we can estimate it using this expected confusion matrix. So accuracy is just true positives plus true negatives divided by the total number of data points. We already have all the information that we need from our confusion matrix. We calculate the accuracy. We have the expected accuracy. That's it. That's really the algorithm, as long as probabilities are calibrated. And which are these numbers here, right? These are the two numbers that we get from the probability. So these numbers, for them to be correct, the probability needs to also be correct. But it's actually not. So how do we know whether the probabilities that our model outputs are actually correct? The way to really inspect that, to find out, is so-called calibration curve, which is exactly what you see here. And what does it display? What does it show? On the x-axis, you have the mean predicted probability of a certain bucket of points. How do we create these buckets of points? We're gonna take a test that we're gonna take a data set that the model has not seen before, such as the test set, so our reference data set. And we're gonna make predictions on the entire data set. Then we're gonna sort these predictions by predicted probability that the model outputs. And then we're gonna aggregate these predicted probabilities into buckets. Let's say the first bucket goes from 0, 0 to 0.1, then the second from 0.1 to 0.3, etc. And then we're gonna calculate the mean predicted probability for each of the buckets. And then once we have that for each of the buckets, we're gonna count the fraction of actual positives that we observe in that bucket, for that bucket in our test set. And if the probabilities are correctly calibrated, what we expect to see that if the mean predicted probability is, let's say, 0.3, then we expect to see 30% of positives for that bucket. But this is unfortunately not the case for vast majority of machine learning algorithms. I believe for everything that's not logistic regression, so gradient boosting models and any kind of ensemble or bagging models, deep neural networks, for deep neural networks is really bad actually. We see either this S-shaped curve or the inverse S-shaped curve. Inverse S-shaped curve really only happens for Bayesian models as far as I know, but don't quote me on that, I'm not sure here. But the point is that we want a straight line, we don't have a straight line. So what can we do? We can actually just make it into straight line with another regression model that we're gonna train on the test set on the reference data. How does it work? So basically, to turn the predicted probabilities into actual probabilities, we only need two steps. First, we're gonna take just one feature, which is the predicted probability. And then we're gonna use that to predict what is the probability of y, so our target, being equal to 1, given that predicted probability. So we're just gonna do one-dimensional regression. We can use any regression algorithm here. We can use gradient boosting. We can use simple linear models, whatever you want. And then we can then straighten the line that you see here. So instead of having an S-shaped curve, you're gonna have a straight curve. Once we have that, we can then say that on the aggregate, on average, and also only for the test set, which is one of the issues with CBP that we solved with our new, better algorithm called MCBP, which M stands for multi-calibrated, that's available in the cloud. But let's assume now that these probabilities are properly calibrated, even if there's covariance shift. And that means that we can follow the reasoning that I outlined on the slides before to get the expected confusion matrix for every point, then aggregate it per chunk, and then compute off the metrics. That's basically how the algorithm works. Now for the results, I wanted to show kind of the opposite case of what you saw for the regression use case. So here, what you see is the PCA reconstruction error, so our measure of multivariate data drift stays constant, stays roughly constant, stays within the threshold. There is no strong covariance shift. But even so, we see a significant drop in the accuracy, and we see that the estimated and realized accuracy follow each other very, very closely. So we're good at estimating accuracy here. And we see that there is a big dip of roughly 20% compared to the test set. So it's definitely business significant, even though there is no covariance shift. So again, if you just monitor covariance shift, you might be, the model might actually be experiencing failure. There might be significant performance degradation, but it's not something you will see just based on the covariance shift measures. That is really it. So now, thanks for listening. We have our documentation that outline the algorithms in detail, both for the cloud and the open source. And as for the cloud, it's something